Yes, so I'm Murray Simons, and I have the privilege of being the moderator for the remaining sessions in this stream. Conscious of time, so we're going to keep moving. We will be taking questions at the end, but I'm just conscious that we need to keep our speed up. So Brenton Smith is our next presenter, as you know from the program, and he is the Chief Technology Officer from Nominal, and his particular interest is in the formation flying of the M2. And the focus is on the stabilisation of the formation. So, without further ado, I'll invite Brenton to come to the stage.
It's great to be here. My name is Brenton Smith. I am the Chief Technology Officer of Nominal Systems, but I've also had the great privilege over the last 12 months of being a research associate at UNSW Canberra, where I was looking after formation flying aspects of the M2 mission that Russ just described. Specifically, I had a great experience doing a lot of the mission planning for the separation maneuver, and that's what I really want to focus on today, because it's a good example of how these types of experiences in sort of pushing, the cutting edge in space can really bring to light new techniques within the industry, through the R&D efforts that stem from those activities. So I'll give a bit of a quick introduction to the M2 again. So it's been quoted as Australia's most complex CubeSat yet. In fact, there's two of them because it's a formation flying mission. So essentially M2 is a 2x12U CubeSat mission. It was launched on Rocket Labs in March 2021. And part of its purpose was to demonstrate technology, which includes the formation flying, which I'll talk more about. So I guess before we continue getting into the nitty-gritty, I'd like to just, give a bit of a high-level overview of how the formation sort of works, just to give a bit more context. So the two CubeSats, they're sort of the boxes, as you might expect from a CubeSat. However, they've got quite a large solar array, which acts essentially a bit like a wing. So the main mechanism that we use to actuate the formation flying maneuvers is through aerodynamic drag. So we're essentially gliding the spacecraft together by changing their attitude, and that changes the drag profile acting on each spacecraft. And so essentially, yes, when the spacecraft are flying in formation, we can use that to actuate the formation flying maneuvers. But the spacecraft were actually launched conjoined. So they were joined together, and that allowed us to contain them as we commissioned systems, which is a typical activity for space missions. So for a period of some months, they were conjoined together. Systems and subsystems were switched on, and they were tested, and at some point we were ready to actually separate the spacecraft. And so it's this sort of separation that my sort of research activities and mission planning focused on. So, and that's mainly because the spacecraft was separated by a spring mechanism. So they're given a bit of an impulse, a kick apart. But as space dynamics go, that initial kick, once has happened, will continue. It doesn't really dampen naturally. And so the question was, okay, so we've got two spacecraft separating after this impulse kick apart. They need to be recommissioned because prior to separation, we had to switch a lot of subsystems off. So while they're almost switched off and separating, we somehow need to contain them as we're switching the spacecraft back on. And that's not a trivial problem to solve. And so I guess that was what we're really faced with. And to give some context to that separation, it was approximately 8 kilometers per day that we were facing. So every day that elapsed, the spacecraft would be 8 kilometers further apart. And if that were to continue, they would just drift apart indefinitely, which is not ideal for a formation flying mission because we want to operate that coordinated formation. And to give a bit of context for what a formation means in space, as Russ indicated with that previous plot, we're sort of talking, from 1 kilometer to 200 kilometers relative distance. So the two spacecraft orbit in the same orbit, almost following the same trajectory. It's just one leads the other about the Earth. And as I described, the spacecraft was switched off, so they had to be recommissioned, which was an extra challenge. So the technique we came up with was actually a bit of a passive stabilization technique, where the spacecraft, when they were separated, were deliberately tumbled. That was to rotate the antennae away from each other to avoid entanglement. But it's also more of a safer operating mode, because when spacecraft are tumbling, at least some portion of the time, the solar panel should be facing the sun, for example. But that meant that we could deploy the solar panels on one spacecraft. In this case, it was a spacecraft with a higher orbit, because as astrodynamics go, the spacecraft with the higher orbit orbits slower. It's got a larger semi-major axis. And that means the other spacecraft will start to pull away from it, and that's what's causing that divergence. But what we can do is, if we can somehow decay the spacecraft with the higher orbit, if we can decay its orbit quicker, at some point the height of the orbit, or that semi-major axis, will be the same. And that way, that relative motion, that divergence, will be nullified. And that's what we really wanted to do. And so, as I mentioned before, the way we did it was to deploy solar panels on one spacecraft only. And this was the spacecraft with the higher orbit. And with that extra drag, it meant that orbit would decay quicker, and it would start to sort of nullify that relative motion. The beauty of this technique was that we could deploy the solar panels and let the spacecraft just tumble. And as they were tumbling, we could do that recommissioning of subsystems. And so there was no constraint on us to have to wait until the subsystems were commissioned before we could start actively maneuvering. So this gave us the benefit of being able to recommission the spacecraft in parallel to starting to stabilize the maneuver. So I mentioned a lot of the actual mission sequence that we followed for this passive stabilization technique. So the other part that I haven't mentioned yet was, obviously at some point in the future, the heights of the orbits will be equal, which is about step 5, you can see in those images. And at that point, we want to reduce that differential drag. We want the drag on each spacecraft to be approximately the same. And so at that point, we deployed the panels on the other spacecraft. So they're experiencing approximately the same drag with no differential drag. And so this was really the technique that we adopted. We did some analysis, obviously, before we did this. And it sort of indicated that given the variance of the delta V from that spring force, we were looking from anything between stabilizing the formation after the separation within a range of 10.5 days to 29.5 days, with a long track separation given by that delta U, ranging between sort of 24 kilometers to 175 kilometers. So we actually did this with M2. So the separation event occurred on the 10th of September last year. And the maneuver was complete on the 2nd of October. So it took 22 days at that point with the separation of 75 kilometers, which for context was sort of within the range that we were expecting. However, as space missions go, it didn't run as smoothly as we would have liked. As Russ sort of hinted before, we issued the command for the panels to be deployed at the end of the maneuver. It turns out that only some of the panels were deployed on the other spacecraft at that time. And so what we thought would be the point where we should cancel the maneuver, we're actually noticing that divergence was still occurring. And so from the 19th of October onwards, we reissued the deployment command, and the rest of the solar panels were deployed. And so we could do the maneuvering sort of nominally from that point. This was only meant to be a high-level overview. So that's the presentation I had for you today. I'm happy to take any questions. Thank you.
So my question's a space weather question. Russ said that really blew things out of the water.
Yeah.
Obviously, we do have access to space weather data, but either we didn't have enough of it, or did you not have access to it?
Yeah, we have access to space weather data. The challenge with a lot of third-party data is the delay, because usually you find out about these things after they've happened, in which case the damage is done, so to speak. So I think a lot of the research effort at UNSW Canberra is focusing on building that space weather expertise, so it can be a much quicker turnaround for reacting to such things. But the processes as well need to evolve. So yes, the data can come in when it does at the moment. I think a lot of the processes in response to that can be optimized. I think we have done that at UNSW Canberra, but I think for spacecraft operation generally, there's a lot of scope for setting up systems to react appropriately to such anomalies. So, yeah.
Thank you very much. So we're talking about the formation flying of the satellite. So I'm curious if you can speak to, what does that formation flying actually allow us to achieve? What are the benefits of formation flying?
Yeah, great question. So a lot of systems are sort of evolving to be multi-agent systems, and spacecraft are no different. For space specifically, the benefit of multiple spacecraft are that you can distribute sensors across the multiple spacecraft. I think, for example, with M2, we have the ability to use some of our radio RAAF observations to cue the trailing spacecraft to take imagery. So they're sort of working in a coordinated fashion. And that sort of scales up to other applications as well. QKD is another one that Russ mentioned. So it was, he had a concept image on his presentation, but it's actually just a quantum key experiment. That's another good example of where a formation can be beneficial, because you can take advantage of the distributed nature of the two spacecraft, and then ultimately you get into the realm of constellations, which gives you quite good revisit times and Earth coverage. So, yeah, too easy.
We're probably out of time there, unfortunately. It's always difficult for someone who's an expert in their field to compress everything down to 10 minutes, so congratulations to all the speakers. If you have more questions, I'm sure Brennan's happy to take them afterwards, and if there are any more online, we'll be able to facilitate that as well. So once again, thanks very much.
Thank you.